it's me, Maria Sandoval, and today I will be presenting on quantum numbers and electrons and valence electrons. So first we're looking at this graph. It shows us the name, the symbol, the permitted values, and the property. I'm going to go from left to right, starting in the first column. The principal is our name, and the symbol commonly known for the principal is N. And the permitted values of the principal are positive integers such as 1, 2, 3, 4, 5, 6, and so on. As long as it doesn't have a negative in front of it, you are good. So the property of the principal is orbital energy, which is our size, basically. Moving on to the one under that in the column, the second column, angular momentum. The symbol for that is L, and the permitted values for that are integers from 0 to n minus 1. I'm so sorry, I forgot to turn off my AC because that is pretty loud. But so integers from 0 to n minus 1, and the property of that is our orbital shape. So the values of L, 0, 1, 2, and 3 correspond directly to S, P, D, and F orbitals, retrospectively, I mean. So 0 is S, 1 is P, 2 is D, 3 is F, so on. So on the third one, magnetic, the symbol for that is ML, and an easy thing to remember is that L is integers from negative L to 0 to positive L. So ML, negative L, positive L, 0. And the property of that is orbital orientation. Then moving on to spin, it's MS, which that one's easy to know because the S is for spin. And then the permitted values of that, which is your spin, are plus 1/2 or negative 1/2, and that is the direction of E minus spin. So here under we have a little graph, just basically using the summary of the quantum numbers that we've just gone over, where we see our angular momentum quantum number changes. It's 1, 2, and 3, and it shows the respective shape of orbitals and the number of orbitals, and then the number of maximum electrons. So 0 has the shape S orbitals, the number of orbitals is 1, and the number of maximum electrons is 2. For 1, the shape of orbitals are P, the number of orbitals are 3, and the number of maximum electrons is 6. For the angular momentum quantum number 2, the shape of orbitals are D, the number of orbitals are 5, and the maximum number of electrons is 10. And then finally, for our angular momentum quantum number 3, the shape of orbitals is F, the number of orbitals is 7, and the maximum number of electrons is 14. So all of this is shown by our graph here, and we got all of that from our previous summary. Moving on, quantum numbers and the exclusion principle. Each electron in any atom is described completely by a set of 4 quantum numbers, N, L, M, L, MS, which we just went over. N is our principal, ML is our magnetic, MS is our spin, and then if we go back, we can confirm that N is our principal, L is our angular momentum, ML is our magnetic, and MS is our spin. We just learned all of this, and these are our 4 quantum numbers that each electron in any atom can be described by. So the first 3 quantum numbers, N, L, ML, describe orbitals, while the 4th quantum number, MS, describes our electron spin. The Aufbau, or the build-up principle, states that electrons enter and fill lower energy orbitals before higher energy orbitals. These are just brief summaries. In the next slide, we'll go into the specifics of these. Pauli's exclusion principle states that no 2 electrons in the same atom can have the same 4 quantum numbers. So an atomic orbital can hold a maximum of 2 electrons, and they must have opposing spins. They cannot be going the same direction. Hund's rule states that when several orbitals of energy are available, as given in a sublevel, electrons enter with parallel spins. Madelung's rule states that orbitals filled with electrons such as n plus L, which, remember, that's our principle in our angular momentum. This rule explains why the 4s orbital has a lower energy than the 3d orbital, and it gives the periodic table its characteristic appearance. Periodic table is based off of a lot of things, and this is one of the things that gives it the shape that it has. So, Pauli's exclusion principle, we're going through these atomic electron configuration and chemical periodicity principles in more detail, principles and rules. Pauli exclusion principle. No two electrons in an atom can have the same set of quantum numbers. So as said previously, if two electrons occupy the same orbital, they must have an opposite spin. For Hund's rule, when several orbitals of an equal frequency are available, as given in a sublevel, electrons enter with parallel spins. For Aufbau, or build-up principle, electrons enter and fill lower energy orbitals before higher energy orbitals. So lower is going to get done before the higher. Madelung's rule is orbitals with electrons as n plus L. This rule explains why the 4s orbital has a lower energy than the 3d orbital, and it gives the periodic table its characteristic appearance, as said previously. Moving on, if it'll let me. Being a little slow today. Sorry about that. I'm not sure. I think my computer might have frozen. So let me just escape really quickly. Okay. So moving on. Splitting of levels into sublevels. Each energy level is split into sublevels of different energy. Splitting is caused by penetration and its effect on shielding. For a given n value, a lower L value indicates a lower energy sublevel. The order of sublevel energies is S, P, D, and F. The n value is constant horizontally, the L value is constant vertically, and n plus L is constant diagonally. Here is a little aid to memorizing sublevel order, so you'll see that the energy of the orbital increases as we go down. So we start off with 1s, and then it's 2s, 2p, 3s, 3p, 3d. Notice that all these ones in the second column are p, and all these ones in the third column are d, and all these ones in the fourth column are f. 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. 5s, 5p, 5d, 5f, 6s, 6p, 6d, 7s, 7p. And as you go down, the energy is stronger. So down here at 7p, 7s, those are going to be your strongest orbitals with energy. Then moving on to our electron configuration of atoms and our orbital diagram of atoms, we're going to be going over like two different ways that our atoms are shown on paper. So this shows the numbers of electrons, the electron configuration atoms. We're looking at this right here. Shows the number of electrons which are indicated by the subscript in each level, describing the arrangement of an electron in an atom. So here's our arrangement. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, 4d5. But we're specifically looking at our 4d5 right here. So here the 5 is the number of electrons assigned to the designated orbital. D is the orbital type, L, and our electron shell is shown by the 4, which is N. So our quantum number set is n equals 4, where n and 4, L equals 2, I varies, and then ms is 1/2. So the orbital diagram of atoms is a different way that this is shown. And this diagram is showing us how the electrons are distributed among the orbitals. So each orbital is represented by parentheses, a box, or a circle, and the electrons are shown by arrows going up or down depending on the spin. So here we have 9F, and we see that up, down, up, down, up, down, up, down, and then just up. We're missing one here. So we're just looking at how these show our different directions and how this staircase is actually showing us the way that our energy is flowing as well. It's placed in that for that staircase way for a specific reason. So moving on, if it lets me. No, I don't think it's gonna let me. So I gotta escape. That is, I'm pretty sure that is the end of our presentation. I'm just gonna double check. Okay, thank you so much for listening to my presentation today. I hope you learned a lot. I learned a lot too. Sorry that my voice has kind of been in and out. I've been pretty sick since spring break. I've been fighting off a little bit of bronchitis, but I will be keeping up with these videos, so stay tuned because I have 2 more. Have a great day. Hope you learned a lot because I always do too.